Hi, everyone. My name is Michelle Suazo. I am the webcast administrator here at the Water Research Foundation. And I wanted to welcome everyone to the fourth and final wastewater process emissions webcast titled Opportunities for Process Emissions Reduction. We have been happy to partner with various organizations to present this series. And as of this third webcast, we have had over 1,600 attendees that have logged in live, and that's not including everyone today, which we have close to 500 registered. So this has been such a great and popular series that we're so pleased to have everyone join us. Before I hand things over to Dr. Harry Zhang, I wanted to run through our housekeeping slide. You are welcome to submit questions through the question box at any time. You'll find that on the left-hand screen. Once we go to a different layout, you'll see that on the left-hand side. So feel free to submit questions, and we'll get to those at the very end during our Q&A time. The slides and the recording of the webcast will be available on our website pretty much after we get done with the webcast. So you're welcome to go there and share the link or look at the slides. You can also download the slides now under event resources on the bottom left-hand side of your screen, once we get to a different layout. And then a certificate of completion is automatically generated after the webcast. But if you have any questions or need any help with that, feel free to reach out to me. My email is there on the screen. One last thing is please stay tuned until the end to fill out a survey. We really do take your comments and your feedback seriously, so we can continue to bring you great webcasts in the future. So we have a great lineup of speakers today. We won't go through their full bios or introductions, but you can see their bios under the bio tab at the top of your screen. Now I'd like to hand it off to Dr. Harry Zhang to run through a few things and then hand it off to our speakers. So Harry, take it away.
Thank you, Michelle. So welcome from the Water Research Foundation. We want to thank you, our partner organization as well. So I want to use maybe 2 slides to give you a little bit update since we had the third webcast about a month and a half ago. So this is my first slide. So I want to use this slide to showing you some of the ongoing research at the Research Foundation on climate change mitigation and also greenhouse gas research portfolios. So we have divided into 3 subcategory in this topic. So the first category, we have 2 active ongoing project. So greenhouse gas inventory and the library. They are focused on one water perspective. On the second category, focus on greenhouse gas field monitoring and also method comparison. So we have 3 ongoing projects in this category. They focus on for example, methane monitoring, nitrous oxide monitoring, which you're going to hear more later at this presentation, this webcast. And also the method comparison. This is for some currently in the proposal stage for both methane and the nitrous oxide. The third category is a focus on multi-criteria decision-making for climate mitigation. For example, how do you evaluate the trade-off among the process optimization, greenhouse gas emission, or even energy efficiency? So this is we want to maybe follow up with you on those projects in the next couple of years. So this is my second slide, also last slide. So I want to mention to the group as we closer to the end of the 2024, Water Research Foundation funded about another 10 projects on the climate change related, including greenhouse gas emission and also climate adaptation. So Research Foundation have a climate change topic hub to capture all this. So here's on your slide, so there's a link to it. So we have so far 80 projects on the climate change studies are focused across one water matrix, focus on adaptation, mitigation, greenhouse gas emission, and also the risk assessment. We're going to adding another 10 more. Going to update this topic hub in the early 2025. So come back to visit us. With that, I'm going to turn to Jessica.
Thank you so much for starting us off, Harry. Hello, everyone. It's great to have you all join us today. My name is Jessica Akonde. I'm a senior program advisor with Canadian Water Network. And so once again, welcome to the very last webinar of this amazing series on process emissions. I am thrilled to be moderating this webinar alongside Harry today. And so before I get into my introduction, I would like to take some time for the land acknowledgement. At Canadian Water Network, we have a corporate goal of undertaking our Indigenous learning. And so you can read the land acknowledgements on the screen. One of the things we have been taught is that we need to speak from the heart. So I personally am on my learning journey, but I am grateful to have the opportunity to work on in Waterloo, Ontario, which is about an hour and a half away from Toronto, at the CWN offices that are located on the traditional territory of the Neutral and Anishinaabe and Haudenosaunee peoples. So today's webinar series and the rest of the 4 series have been put together by a great collection of organizations. So it's organized by the US Water Alliance and Canadian Water Network, and it's being hosted by the Water Research Foundation in collaboration with the International Water Association, as well as the Water Environment Federation and the Danish Water Technology Alliance. In Canada, our federal government has a goal of reaching net zero by 2050. But in the interim time, the goal is to reduce greenhouse gas emissions by 40 to 45% below 2005 levels by 2030. And so Canadian Water Network, as a not-for-profit organization, is working to facilitate knowledge mobilization between municipalities and water utilities. We tackle complex water-related challenges that affect our communities, our health, and our climate by bringing together leaders from different parts and fields and sectors to learn from each other and share their knowledge, as well as work together to make a difference. And so CWN is working, in this field, the Water and Climate Program. And under that Water and Climate Program, we're working towards resilience, adaptation, and mitigation. And for the whole webcast series, it has been our goal to deepen the understanding of greenhouse gas emissions from treatment processes. So we have spoken about the types and sources of greenhouse gas emissions. We have also talked about mechanisms and process conditions, and we have gone in depth on quantification, measurements, and monitoring techniques. We have discussed a little bit about emissions and reduction strategies, but today is all about the emissions reduction strategies for sure. So the first webinar took place on July 19, where we discussed the fundamentals of process emissions from wastewater treatment plants. And we also talked about methane emissions on September 18, nitrous oxide emissions on October 31st. And today we're talking about mitigation strategies. And a very quick recap of what we've heard. So the very first webinar, we heard about nitrous oxide and methane emissions from wastewater treatment plants becoming more dominant across scopes 1, 2, and 3 emissions as more water utilities switch to cleaner and renewable forms of energy. We also heard about multiple methods that are required to identify and quantify actually both methane and nitrous oxide emissions, plant scale and site scale. And then we also identified that there were uncertainties associated with measuring nitrous oxide emissions. But the bottom line is we know enough to start measuring and mitigating nitrous oxide and, to be honest, methane emissions right now. So our goals for this particular webcast, we're exploring strategies for reducing nitrous oxide emissions at wastewater treatment plants. We'll also like to deepen our understanding of how emissions reductions can be implemented through case studies and examples, with the hope that this, spreads out to other kinds of emissions as well and greenhouse gases. So our agenda for today is that we have our mitigation inspiration by Jose Porro from Cobalt Water Global. We have opportunities for nitrous oxide mitigation by Nerea Re-Kerenium, as well as nitrous oxide emissions again from Jens Monk Poulsen. And so with that, I'd like to hand over to Jose to take over and get started.
Thank you, Jessica. Yeah, so hoping to provide some inspiration for mitigation for the scope 1 emissions. We're really focusing on nitrous oxide and methane in this webinar. And as Jessica mentioned, this is the last webinar in the greenhouse gas series, and it's focused on mitigation. But I think it's also a good opportunity to bring everything together, because as nice as it would be to snap our fingers and immediately start mitigating, there's a lot that has to have taken place and a lot that has to be taking place in order to have successful mitigation. And it really starts with planning. So a lot of people think that the first thing you need to do is to measure. Well, that's not true. The first thing we need to do is find out where we need to go and measure and reduce first. And this is done through using different tools to really assess and determine where the biggest potential for emissions are and the biggest opportunities to reduce emissions. But then once I've identified where we need to be going first in a prioritized way, because we don't want to be losing time going to places where to measure and find out that we can't do anything, because we can lose a lot of time and we're under a tight timeline. But once we've identified where we need to go, we can do the quantification and the measurements. We've seen the previous webinars cover on this, but also using different tools, mitigation, implementing the mitigation actions, verifying the reductions, and then monitoring after reducing, because we don't want to reduce and then forget about it, or as we say here in Brooklyn, forget about it. We don't want to forget about it. We want to continue to monitor and continue to verify that we're reducing, because it can change. So once this planning has really set the program into motion, what's important to be able to implement this at scale and effectively and consistently is to be following best practice. So we have reached a point where we have best practice in the industry, and we have different levels of guidance documentation for this best practice. We, as a company, we have our own protocol that we follow in terms of sensor placement, sensor maintenance and calibration, the dealing with data gaps, verifying the accuracy of our models and maintaining the accuracy of our models. So it's really important to have something to follow so we can do this effectively and consistently. But it's also important to be leveraging the tools that are available. And as technology providers, we want to be providing practitioners with the best tools so the mitigation can be achieved effectively and efficiently, because again, we're under a tight timeline. In these next two slides, Amanda Lake from Jacobs provided based on the work that they're doing in terms of decarbonization. And here's a hierarchy of methane mitigation strategies. And it really boils down to avoiding, reducing, and removing. I won't go to the individual actions for each of these into any detail, but what's important to keep in mind is that these are examples of what has worked. It doesn't mean you have to do all of them. In fact, in some cases, it may not make sense to do some of them. So the important thing is to do what makes sense for your situation. And it's exactly the same for N2O. We want to be avoiding, we want to be reducing, and we want to be removing. And again, there's various actions that can be taken for each of these, but it's important to do what makes sense for your situation. So getting back to the other components that are necessary for mitigation, for example, knowing where to go first to mitigate and using machine learning for this. So we provide machine learning tools to be able to do this. And we borrowed a concept from tracking of hurricanes, the use of these spaghetti models. So for tracking hurricanes, they run various models that are out there, the European model, the US model, and others, to find out where there might be consensus among the models. And then where there's consensus, this is where they issue the warnings for the hurricanes. So we can do the same with N2O and machine learning models by using an appropriate set of models based on the process conditions and the pathways that we know are occurring. We can see where there's consensus among the models and then be able to use this instead of using generic emission factors to tell us where we need to be going first. It also helps to get a good estimate of the N2O emissions, but it's not intended to be perfect. The idea is to help us guide us where we need to be going to measure and reduce first. So this is using machine learning, but we also can use AI for this. So we use knowledge-based AI to quantify the risk of N2O formation. And this is using data, so for example, dissolved oxygen, which is widely available and is also the most important factor because it will dictate which pathways will be occurring. So we can use this, we've used this to identify mitigation strategies at a granular level, but we've seen that zooming out, it is also helpful to tell us where we need to be going first, because we've seen a strong correlation between the risk and the calculated N2O emission factors using the measurement data. We also have seen that this works even better if we take into account removal efficiency and the population equivalence, because the removal efficiency is a measure of how hard the plant is working. The overall risk tells us under what conditions it's working hard or not working hard, and the population equivalence is an indicator of the load, how much work is actually being done. So doing a lot of work in the Netherlands over the years, we've been able to validate this. So we also can use AI. Once we're at a specific site, now we know where we need to go. We can use AI to help us identify mitigation strategies. A lot of times we look at data like this, or we have N2O measurements, and we plot it with process data like the dissolved oxygen and the ammonia. But we're in 2024, which if AI can make our lives easier, we use AI. So we want to use AI for N2O. And if we look at the risk, if we plot the risk now on top of this, it boxes out exactly where you have the problem, N2O increasing. And at this level, it's kind of hard to see what might be going on, but we can use at this level the outputs to verify that this is a pattern. We see consistently N2O going up under these peaks of risk due to high DO conditions. But then the idea is to zoom in to one of these peaks and see exactly what's happening. So here we're converting ammonia under this peak of high DO risk, and we see the N2O coming up as this is being converted. So we know that this is because the DO is too high. So we look at the DO and we can see at times it's going up as high as 3, and we can see what the recommended DO is. And the idea would be to still bring this ammonia down, but avoid this N2O from increasing. And we've achieved up to 90% reductions following this in summer, winter, fall conditions. So it's now just a matter of doing it. Something also that's really important to keep in mind is the use of emission factors, or should I say the misuse of emission factors for tracking and verifying mitigation. Because we've seen cases where if we're tracking the emission factors and the risk and the emissions, we can see how the emission factor changes over time, which we know to be true. But we also see cases where the emission factor can actually go down, but if you see here, the emissions are actually going up. And that's because to calculate the emission factor, we're taking the load into account. So depending on the ratio of the N2O emissions and the load, you can have a situation where you have an emission factor go down, but your emissions actually go up. So for tracking mitigation, it's important to track the actual emissions. But again, it's also helpful to look at the risk, because the risk is, we see consistently be a good indicator. And so we're also thinking about how to measure and verify the reductions. And the current thinking now is that you have to measure for a full year and then take action, because then whatever reduced emissions you have after implementing interventions, you're comparing to the previous year's emissions where you didn't implement interventions, but you lose a whole year by following this. So what we do is we baseline and reduce at the same time. So we designate one lane as sort of like the control lane, where we don't touch it. We're monitoring the N2O in this lane, and the parallel lane. All the other parallel lanes, we implement the interventions and are monitoring physically. So you see red are with physical sensors, but because we're always limited by cost, we also are using machine learning soft sensors, which are the purple ones, to verify what's happening in the other lanes and to verify that we're continuing to reduce. So the key takeaways are that mitigation is an ongoing journey. It's continuous, it's not finite. It's important to follow best practice. It's important to leverage the tools that are available so we can do it effectively and efficiently. It's important to know where to go so we don't lose time measuring where we can't implement mitigation actions. And it's important that once you are at a site that you're baselining and reducing at the same time so we're not losing a year. When tracking emissions, we want to track the actual emissions, or tracking mitigation, we want to track the actual emissions and not the emission factors. We can track both, but if we want to verify mitigation, it's important to track the emissions. We see that AI and machine learning can be invaluable tools. It's also important to recognize that we now know enough to start taking action and implementing these technologies and applying this knowledge in practice. We no longer have to wait for research to take action. We can continue research to advance the technology, advance the knowledge, but we don't have to wait to start taking action. It's important to keep in mind that it's not just about reducing. We should be looking to avoid, reduce, and removing. And it's important to keep in mind that we are under a tight timeline, and that every ton of CO2 counts. There's a lot of focus on the contribution for different sectors, but it's not about what one sector is contributing. It's about reducing any ton of CO2 that we can reduce, because the atmosphere doesn't care where it's coming from. And if some of you have watched the show, The Bear, a motto that is recurring among the series is that every second counts. So I was inspired by this and was hoping that it will also inspire others to do what they can within their organization to get things going and make every second count. So let's get to work. Thank you. So I'll pass it on to Nerea now.
Thank you, Jose. Yes, am I on screen now?
Yes, you are.
Okay, thank you. Good morning, good afternoon, or evening, everyone. My name is Nerea Carreño. I am the founder of N118 Consulting for the past 4 months. Before that, I was working with the Danish utility for 11 years, VCS Denmark. And through my job, I had the opportunity to work with a lot of new technologies and a lot of exciting projects, and had the chance to work a lot with greenhouse gas emissions, and particularly with N2O. So I want to start by taking us back to why are utilities doing this today, and want to remind us that this is, until now, very much voluntary efforts done by utilities. We might have legislation coming to Denmark next year, but we still don't know how that's going to look like. But it's motivated mostly by decarbonization goals. And if we look at the big scheme of things, N2O from the wastewater sector might not be a huge contributor, but when we look at specific facilities and specific utilities, then N2O can make the largest can take the largest contribution, and that's certainly true for the Nordics, and that's why it's been such a hot topic for the past decade or so. So before I start going into mitigation options, I wanna go back to this mitigation hierarchy. This is slightly different from the one Jose presented. The way I look at this, we have a wastewater treatment plant, and we don't know yet how to do nitrification and denitrification without any N2O. So the only thing that we can do to really avoid N2O is to get that nitrogen not coming to the wastewater treatment plant. Once that nitrogen is in the wastewater treatment plant, we have our technology that we have, the infrastructure that we have. So all we can do is try to reduce that. And we have a few handles that we can do to that. We've got mostly ammonia, dissolved oxygen, biomass, and carbon. And it's not like those are the root causes for the N2O, but those are the handles that we can play with to mitigate mostly. And then we can go into treatment of the exhaust. And then another option, maybe more for the future, I think, is looking at replacing technologies. So looking at technologies that by default might be producing less N2O. But today we're gonna focus a lot on reduce. And you've probably been presented this a million times. We know N2O is produced both during nitrification, denitrification, and although it is extremely complex, I think we understand now enough that we can point out the causes for N2O in most cases, and even without having any monitoring, we can. With AI, as Jose does, or just with old human intelligence, just look at the potential risk for N2O. So we know which conditions are likely gonna give us N2O, are gonna get our system out of balance. So this is an exercise that we did with Watercare in Auckland, New Zealand, for their nitrous oxide emissions strategy that was published this year. And this document is public and open. And so looking at the processes and where the risk was and trying to put together a list of mitigating actions, even before there was any N2O data, put together a list looking at these few handles that we have. What can we do in terms of aeration? What can we do in terms of ammonia management, carbon, biomass, which mostly is SRT control, and then looking at what is the potential that these actions could have, and what is the actions the utility could take. What are the constraints? Usually when we work with N2O, we find out that sometimes equipment is limiting. Blowers that are too big or too small, valves that cannot do what we want them to do, etc. Now I'm going to present a couple of examples from my work at VCS over the years. This is a very, very old example, working back with the SideStream Anamax reactors. I think this is 2017. We've always had very high emissions from these SideStream reactors, mostly because of probably the way we operate them. But they've been historically very high. So we've tried over the years a couple of different projects to better control these reactors, and we've managed successfully to come down in those emissions. And when we do these projects, we're always looking at these co-benefits. So we want something that's going to reduce N2O, but it's going to give us at least the same performance, effluent quality, and looking if it's even, like in this case, it was slightly better for energy use, all those co-benefits that I think usually come with reducing N2O. This is another example. This is from this summer, and in this case, the N2O reduction was almost a side benefit of getting the reactor back in balance. I think especially when we have very high emission episodes, it's usually the system not not being in steady state, being out of balance. There's something usually wrong with it. In this case, it was pH. So around July, just by going into the controls, changing the set points, getting that pH and that DO where it should be, the nitrogen removal started going up. So the tank had been, like, the reactor had been struggling for a while, and all of a sudden, like, the performance was going up, N2O goes down. In this case, it's almost a side effect of getting your performance right. This is another example from the mainstream at IBMULE, also with VCS. This is a funny example because we were monitoring the reactors because of a national emission campaign. So we were supposed to get the national emission factor for Denmark. And when I get the data set, I'm like, wait a second, there's something wrong here around May. What happened? There was a lot of N2O, like a lot of N2O. And turns out operations had changed the reactor operations from parallel to series, and they didn't change the controls. So they didn't change the aeration. So before we had these two reactors working in parallel, very steady, very happy, nitrate under control. And when they change operation without changing the aeration set points, this one reactor now gets double the load, and it's trying to keep the ammonia in place. And of course, it's working over time. It's stressed. It was producing a lot of N2O. So again, usually good N2O comes with good performance. And these examples are just all the human intelligence and process engineering, but there's, as Jose said, there's commercial solutions, and he's got one. AM team has a combination of CFD and biokinetic. There's the twin plant with DHI, Veolia, and Viden. I think Jens Niras is going to present. So there's a lot of solutions out there that are going to come implementing controls that are specifically tailored for N2O. And I think we're already seeing a lot of success in here. If we move forward, we are looking at past, we've done everything. We've reduced all we can. What are the next things we can do? We had this project last year where we tested catalytic treatment of the exhaust. And we saw that for very specific cases, in our case, for our side stream, and potentially maybe, I think, MABRs with very reduced airflow streams, this is going to be a very interesting solution for the future. But it's going to come at a cost because we have to heat up the gas up to 400 degrees. There's a cost associated with it. So potential for the future, but the feasibility, it's going to have to be, it'll be very case specific. We've done a lot of reduce. The next thing, also, I think looking into the future, at some point when we get confidence enough that these technologies really are better than something we're comparing with, like, for example, one-stage side stream versus two-stage side stream, or MABR, which I'm not sure is fully proven right now that is better for N2O, but if there's one technology that I think has the potential to be better than the other ones intrinsically for N2O, is probably MABR. Take-home messages. This is still very voluntary for utilities out there, so it's all out of goodwill. A lot of utilities doing a lot of good work. We usually get win-win situations when we start looking at N2O, when we learn more about our processes and we get co-benefits out of it. There's a lot of already, I think, successful case studies out there, but you're not going to find them on peer review. I think if you do a literature study, you're not going to find them, but because they're now at commercial stage, but there's, several companies already working with this, and also utilities doing it in-house. I think once these technologies and processes get more mature, I think utilities are going to have to look at what is the price the N2O that we're mitigating, so that we are making smart decisions on this area. Yes, that was it. Thank you very much. And now I'll pass it on to Jens.
Thank you very much, Maria. My name is Jens, and I'm a process specialist and team leader at nitrous, a Danish consultancy firm. And I have been involved in the nitrous oxide games for quite long, starting with sensor development, and recently done some studies for the Danish government in how to implement national guidelines for nitrous oxide emissions. And actually, that kind of report has just come in an English version. So if everyone is interested in how the Danish government is going to limit nitrous oxide, you are welcome to contact me. But I'm going to talk, like Nerea said, a little about and how to reduce nitrous oxide in a traditionally biologically system. And by that, the purpose is to be able to do advanced control, to increase the biological capacity and efficiency of the purification process with some simple controls at a wastewater treatment plant. So the base of this is actually to use simultaneously nitrification, denitrification, trying to control the ammonia rates to be as small as possible. And when we do that, we get a smoother moving. Sorry, I just need to go there. Yeah, so we have made a PSD regulations directly in the PLC of a treatment plant to try to make the rates of ammonia and nitrate be the same. And when we do that, we know that the ammonia oxidation rates, the lesser, if you can decrease the ammonia oxidation rate, we also can decrease the N2O production. So to do that, we see it's been a tactic, but actually we just are getting more flayed weights and less oxygen in the tanks, but at the same removement efficiency. And when we do that, we get a lot better solutions for nitrate reduction. So I would briefly take you through the results of the nitrate reduction. So we have done two similar periods with same load and same setup in the PLCs of the SCADA system. And when we do that, we get a much lesser nitrous oxide emission. So the dark blue one is the baseline for ordinary control, and the light blue one is the one when we do a rate control based on ammonia. And if we do that, we get lesser nitrous oxide emissions from the process tanks, and we're actually going to save about 60% of the nitrous oxide climate, and that equals about 470 tons of CO2. Yes, that was a short brief on how to try to mitigate with existing equipment, and we think we have been pretty successful in this, and actually shown that even that they are getting new limits for nitrous oxide in Denmark. At this plant, they are not getting a high bill because of the pre-phased mitigation. Thanks. I think I should give the word further.
All right. Thank you so much, Jens. So I'd like everybody to come back online if you can, all the presenters. And so we have a few questions. We have a lot of time for questions today. That was our intention. So Jose and Nerea and Harry, if you all come back online. Okay, so there's one very interesting question that came in quite early, and I'm guessing it's geared towards Jose, but Jens and Nerea could answer. Someone said, could you please explain in a little more detail or use examples of what has worked for you in terms of AI? What kind of AI have you used and what has worked so far for nitrous oxide emissions?
Sure, I can answer. So we specifically use knowledge-based AI, which essentially mimics the reasoning process that an expert would follow in looking at data and being able to say whether there's risk of N2O formation or not based on the knowledge of the pathways and the influencing factors. So it can also be called an expert system because it's basically almost the same as having a robot do what you would do in looking at the data. But obviously, since it's a machine, it can do it much faster, much more consistently. And when we're trying to do this at scale, it's important to leverage the power of AI and machine learning. But in terms of what's worked, in terms of using the knowledge-based AI, we know based on whether it's the DO, nitrite, COD to nitrogen ratio, pH, at what concentrations or what levels of these parameters are you going to have higher N2O formation and lower N2O formation. So if we quantify the risk, we know what's contributing. And then once we know what's contributing, we know what needs to be mitigated. So we can recommend DO, and we've had a lot of success with just optimizing the DO, and I would highly recommend starting with looking at what your DO is, because if you can simply change it to lower the risk, we know if you lower risk, you lower N2O. But if you can't change it, at least you know where you stand, and you can start to look at other factors, which we could call secondary factors that can affect the DO and also the metabolism of the bacteria and their propensity for producing N2O. So even though you might be limited in what you can do in terms of adjusting DO, you might be able to adjust MLSS. And there's multiple cases of where adjusting MLSS helped reduce N2O. But you have to look at where you stand with the DO, because sometimes increasing the MLSS can help, but sometimes it can make things worse. Same with decreasing. But there are multiple levels. I think another big one is looking at internal recycles. A lot of times we're sending back high DO to our anoxic zones, and that's impacting our denitrification. So that leads to high N2O production in the anoxic zones. And then when that goes into the aerobic zones, that gets stripped out. And we've seen high correlation between the N2O in the anoxic zones and the N2O in the aerobic zones. So I think those are some examples.
Thank you so much, Jose. And so that came across strongly throughout all your presentations, the impact of reducing one, and you see the effects, especially through Nerea's presentation, came across strongly. And so the next question is for Jens. Jens, you are being asked to elaborate more on how you control your ammonia oxidation rates.
Yeah, so we actually calculate, the movement in the ammonia sensor. So take the ammonia at N0 and the ammonia at N-1 and make a rate. And then we say the rate of ammonia is the set point for the aeration system to make the same rate for nitrate. So every time you have, increasing ammonia, you ask the aeration system also to increase the nitrate.
Thank you very much, Jens.
That's actually what we're doing. Yeah.
Thank you. And I'm going to put the next question to Nerea because you're the one that used the words that was asked in this question. It says, can you share one of the commercial case studies of successful mitigation as a technical report? Like, so what examples of case studies are out there? Because you did mention that there are a lot of case studies. And I guess people are asking where they can find that.
Yeah. Where can they find it? That's the hard part, right? Like, it's not peer reviewed. So if you look at peer review, you're not gonna find a lot of either long-term campaigns. That's also I think missing. There's so many utilities now that have equipment and have been monitoring and have been mitigating. I think not a lot of it is published. I think now it's in the hands of the technology suppliers. I mean, this is not true. I was in Australia a couple of weeks ago, and there were like several presentations, and there's utilities like the guys in Finland, for example, that have done a lot of work on mitigating very successfully. There's a lot of examples in Denmark. There's reports that are available, I think, in Danish for Danish case studies, and I'm pretty sure all of the vendors will be happy to share with you if you contact them, for sure. Yeah.
Yes, thank you. And so, Jose, Jens, do you have any additional places people can find resources? But before you answer, IWA does have a process emissions working group. And so they get to share a bunch of case studies there. I think I couldn't attend the last one, it was at 4 a.m. my time, but they do share some case studies. So Jens, Jose, any other resources where people could find these case studies?
I think Maria has said it. So there are a lot of things going on in the Danish utilities, but again, I think most of it is in Danish.
Mm-hmm.
So you'll need to translate them. But I said before, the main report for regulation will be released in English in short terms, and there are some issues about what kind of sensors can be used and or what are the recommendations for what sensors can be used to calculate emissions, and also how to what can be reached at a reasonable economy based on how many CO2 equivalents can be mitigated to a given cost. So we've worked with two setups as a low cost and a high cost, also. So there should be inspiration for how to further mitigate.
And so, Jose, I'm going to go to the next question. And so this applies to any one of you, to be honest. On that topic of cost, a question is asking, have you found opportunities that reduce operating costs as well as emissions? So back to that, question of co-benefits. So while you're reducing those emissions, have you found any of these solutions to reduce operating costs as well?
Yeah, I think we have. So I actually showed an example where there was N2O because the dissolved oxygen was too high. So to fix that, it require reducing the dissolved oxygen and the aeration and the energy consumption. So we've seen cases where energy has been reduced, not by huge amounts, and same going the other way. Sometimes the N2O is because there's too little oxygen, and when it's been needed to increase the aeration, it does increase the energy consumption and cost, but not by a lot. But I think in terms of, reducing costs, that there's certainly plenty of examples where you have N2O due to high DO, and you're going to have not only the reduction in N2O, but the reduction in operating costs from lower energy consumption.
Okay, that's a good one. Anybody else? Operating cost reduction alongside emissions reduction?
I think that's the perfect case. Like, that's the perfect scenario, and that those are the best ones, right? But I think sometimes it's going to go the other way. And when we start talking about carbon addition or alkalinity addition, or like the case I presented where we're like going one step further and looking at N2O removal with catalyst, there's going to be a cost associated with it. And even everything that we're doing with sensors and so on, everything has a cost. So I think that's part of the equation, I think.
Yeah. All right.
I guess a key point.
And so it's not just, oh, sorry, go ahead.
Yeah, sorry, I just wanted to add before we move on. I think a key point also is to remember that a lot of times, in most cases, the water utility will have to meet some net zero target. And to reach net zero, you have to do something about the N2O. And you could either reduce it or to reach net zero, offset it on paper by doing something to offset it, either purchasing carbon credits or taking some action internally that can offset those N2O emissions. And most of the time, those offsets are going to be more costly than just reducing. So even if reducing means increasing your cost a bit because of more chemical addition or more energy consumption, I think you really have to look at the whole life cycle to determine whether it's more costly, which I would think in most cases it's always going to be more costly to buy offsets than to just reduce.
Yeah. And so it's not just about the money, right? It's also about the co-benefits, the improvements to society, the environmental benefits. And so in the perfect segue, another question is asking, what approach would you use to remove or reduce ammonia and nitrates to meet effluent permit requirements and reduce nitrous oxide emissions? So how do you do that, reduce those effluents alongside? So people are interested in those co-benefits that have been mentioned, but looking at it now from, I guess, the effluent requirements. Yeah, go ahead, Jens.
Yeah, but when we do the nitrified denitrifier, we actually get 30% less total nitrogen out of the plant. At the same time, we're reducing the nitrous oxide by 60%. So it's not a or else. It can be a win-win. But then there are some other disadvantages. For example, if you have a large BioP, then you are going to use a lot more ferric for phosphorus removal. So I think that the main topic is to make some goals on where we want to be, then chase them. And every time you chase one way, there's something that goes the other way.
Of course. And there's a question here specifically addressed to Jose. They're saying slide 26, you measured that the emission factor comes down, but the actual emissions are going up. Could you please provide an explanation for this? I guess it's talking about the mismatch between emission factors and actual emissions.
Yeah, because the most standard way of calculating the emission factor is calculating what the ratio is of the N2O emissions in, say, kilograms per day versus the incoming nitrogen load in kilograms per day. So depending on what that ratio is, because the load can always change, you could end up in a situation where you have emissions actually go up and the emission factor go down because of the changes in the load. So it's really strictly a function of how the emission factor is calculated. So that's why it's important to also look at what the actual emissions are.
Yeah. All right. And then one more question before we go to our concluding slides. It says, in discussing the usage of AI to determine areas for emissions reduction, could you discuss the emissions associated with the high energy usage of most AI platforms? So that's outside the scope, but that's something that I guess needs to be discussed. To say, while we're using AI, I think it goes back to Jens' point of while you're reducing, something goes up. So I guess one of the things that goes up is the energy used with AI. And so I guess I just wanted to have your take on what that, how you account for those emissions.
Yeah, so we've been looking at that, and we can we use Amazon Web Services for all our cloud computing. So they're able to give us those numbers, but we are an early stage startup and are ramping up, so we're not yet at critical mass of where those emissions are high enough, but it is something we need to keep an eye on, because the idea is to reduce as much N2O as possible, as fast as possible. So as we add more and more wastewater treatment plants to our platform, the higher those emissions are going to go up. But I think it's really about understanding what the individual cloud service providers are doing to minimize their emissions, and working with the right ones.
So thank you all. Amazing presentations. I learned a lot today. You know, even from identifying those co-benefits to being able to understand that every carbon dioxide equivalent counts. So that's something I'll probably be using. I'll probably steal that from you, Jose. But very interesting conversation. I really love that the three of you were able to make mitigation seem more approachable than it usually is. It's not, you know, it's complicated, but it's doable. And that's what I got out of these presentations. So thank you all. And I'm going to have Harry come on screen as we talk about the last couple of slides. And so thank you to our presenters.
So this is ongoing work on the resources. I think, Jessica, we can tag team if needed, I guess. So I'm going to talk about, I think, as we mentioned, there's you know, the resources climate change topic hub from the Water Research Foundation, and also climate change related project in there. So I think maybe Jessica will tag team. Maybe you can go over some other resources. I think you know, if you need some other information, I can help.
Definitely. And so you can get involved if you're in US. You can get involved with the US Water Alliance. They have a discussion around why water is a crucial pathway for addressing the climate crisis. All these links are accessible in the presentations that will be sent out later today. And you can also follow them on LinkedIn. At Canadian Water Network, you can get involved in our Net Zero Water Network. We just started, was just launched a couple of months ago. So please click that link, get to know what the project is, get to join and follow along with our progress, both on that site and on LinkedIn. And also you can go on the Danish Water Technology Alliance, who have really come through for us in this particular series with the mitigation part of things. And so you can keep informed on their website. That link is also available, or follow them on LinkedIn. And so do you want to take over this, Harry? I feel like this is within your wheelhouse.
Okay, so I think we're at the so, and also from the Water Environment Federation, who is sort of a partner organization with Water Research Foundation. So there's a greenhouse gas focus group there, and then the group actually met just this year at the annual WebTech annual conference called WebTech in New Orleans. I think there's also the link here for getting involved. I think and then you can sign up, I guess, about getting the email from them. And also International Water Association, also another partner. I think one of the great example is in August this year, there's a World Water Congress. There's lots of program sessions, workshops, including from the International Water Association task group, and also committees, and then by lots of volunteers who support this webcast. So we want to thank you for all of them. Yeah.
All right, so we want to say thank you to everybody. Our presenters did an amazing job. All the presenters, not just from today, for all the 4 different webcasts. Please keep in touch. Click on the links. If you'd like to get in touch with US Water Alliance, please click on that link. With Canadian Water Network, please click. And those resources from IWA, please click on it. Join the groups if you can. And we are very, very excited to wrap this up finally. And so we just want to thank everyone for joining us. Have a wonderful rest of your day.